Hi, welcome to lesson 6.2, Bisectors of Triangles. Now, in preparation for this lesson, you're going to need a few things. You're going to need a few pieces of half sheets of paper and some graph paper, as well as your compass and protractor. Okay. The first piece of half sheet is going to go on page 169. So grab a blank sheet of paper, cut it in half, and then put it right above that. And we're going to be doing a construction on this page and on the next page. So on page 170, please make sure you put a half sheet of paper right there. Okay, so pause the video and continue as soon as you're ready. Okay, on page 171, you are going to put a little piece of graph paper. So make sure you have some graph paper. And you're going to cut that into thirds. Okay, look on my website and I'll show you guys how you guys can achieve that. Okay, so that is for problem number 2. And then down here at the bottom, we are going to do problems 1 and 3, and this is on page 171. And on page 172, you are going to be doing number 4 right there. So go ahead and do that and then pause the video and start it whenever you are ready. Now what we're going to do is we are going to start on page 169. So go to page 169. Now the first construction that we are going to do is called the circumcenter. Okay. Write that down. Circumcenter. Okay, and how are we going to achieve finding the circumcenter? We are going to be doing the perpendicular bisector of the sides. So we're going to achieve that by doing the perpendicular bisector of the sides. Now, here's the thing. Obviously, triangles have 3 sides. We don't need to do the perpendicular bisector of all 3 sides. We really just need to do 2 of them. So in order to do this, here's what you're going to need to do. First thing you need is a triangle. Now, if you're doing an obtuse triangle or a right triangle, you're going to get different results, and that is okay. We're going to talk about that in a little bit. So I'm going to do an acute triangle because it's the easiest one to demonstrate. So I'm going to draw an acute triangle, and you do the same thing too. Try not to make your triangles look too equilateral. Okay, something like that. It's not equilateral, but it's also not too not equilateral. Okay, we're going to call this A, B, and C. And what I want to do is I want to do the perpendicular bisector of every side, at least 2 of the sides. Okay, so we're going to use our compass for that. So I'm going to do this for, let's start with AC. Okay. So I want to do a perpendicular bisector of AC. So I'm going to open up my compass to a distance that is more than halfway. This is almost halfway, so maybe just a little bit more. Okay, so what I'm going to do is I'm going to draw 2 arcs, one from A and one from C, such that the 2 arcs will intersect each other. So remember, move the paper, not the compass. Here is one, and now I'm going to do it for C. Okay, just like that. Okay, now once you do that, go ahead and mark the perpendicular bisector like this. Okay, just like that. This is going to be perpendicular, and this segment right here is going to be congruent to that segment right there. Now, repeat the process for a second side of your choice. It doesn't have to be any specific side, just one of the sides. So I'm going to do AB. Okay. Now, what I want to make sure is that I don't have the same distance on the arcs as I did over here, which most likely it's not. You're going to have to open it or close it. So I'm going to go ahead and open mine a little bit more. Okay, and I'm going to make an arc both from A and from B. Like this. Now what you're going to do is you're going to draw a line between those two intersections. Okay, so this is perpendicular, and now you have this side congruent to this side. But what we are paying attention to more is this point of intersection right there, where the two perpendicular bisectors meet. That point is called the circumcenter. And I'm going to call that, I don't know, E. Okay, I'm going to call that E. So here, E is the circumcenter. So what's so special about the circumcenter? Well, here's the fun part. Okay, I want you guys to put your compass on E. And I want you to open it up to the distance to one of the vertices. Doesn't matter which one. From here. Okay? Now check this out. It's pretty much the same thing. Okay, so what is the circumcenter? The circumcenter is the point that is equidistant to the vertices, meaning this. Okay, I'm going to do this with a highlighter so you can understand what I'm talking about. Okay, the distance from the vertice to E, from the vertice to E, and from this vertice to E is the same. All three of these are the same. Okay, so this is the point that is equidistant to the three vertices. Okay, so you have EA congruent to EB congruent to EC. Okay, now how did we achieve this? By doing the perpendicular bisector of the sides. So this chapter deals with centers of triangles, and there are 4 centers of triangles we're going to learn. This is the first one. It's called the circumcenter. And you achieve that by doing the perpendicular bisectors of the sides. Okay, so you guys have to remember that the circumcenter is equidistant to the vertices. Okay, so that's one thing that you guys have to remember. Okay, the circumcenter, if I can spell circumcenter, the circumcenter is equidistant to the vertices of a triangle. Now, Mr. Osuna, what happens if I have an acute triangle? What happens if I have an obtuse triangle? What happens if I have a right triangle? Your circumcenter is going to be different for all 3. In this example, we have an acute triangle. Okay, so it just so happens that when it's an acute triangle, the circumcenter is going to be inside the triangle. If you were to have an obtuse triangle, it will be outside of the triangle. And if it were to be a right triangle, it's actually going to be on the hypotenuse. On the hypotenuse. So if we, in class, I'll probably show you guys with a demonstration, but here are the 3 different ways. In this case, we have an acute triangle, therefore the circumcenter was inside. If we had an obtuse one, this point would be outside the triangle. And if this triangle was a right triangle, that point will be on it. Now, this is still true, though. This part right here, it's still true. So this is the first center of a triangle that we learned so far, the circumcenter. Let's look at the second one. Turn the page. Okay, so for the second one, we are going to learn about the incenter. Okay, so far we've done circumcenter. Now we are doing the incenter of a triangle. How do we achieve that? Okay, well, we achieve that by doing the angle bisectors. Okay, the angle bisectors of every angle. Okay, we're only going to do 2 though. No wonder our last lesson had to do with perpendicular bisectors and angle bisectors. It was in preparation for today's lesson. So, what do we need to do? You need a triangle. Okay, so let's look at this. Okay, just like this. And we're going to call this triangle A, B, and C. Okay. Now what we're going to do is angle bisectors. All right, we're only going to do it for 2. Okay, so if you forgot how to do an angle bisector, pay attention. Okay, so first thing is create an arc from B, like this. You can keep the same distance if you want. You can change it, totally up to you. From this intersection, create an arc in the middle, and then do it again for the other side. Boom. Okay, just like that. I have to create a shadow so that it's stronger. So then once you do that, create your angle bisector, like this. Therefore, this angle and this angle are congruent. Now do it again. I'm going to do it for A. If you hear noise in the background, that's my kids. Okay, do it for A. Like this. Do it again. And do it again. Angle bisectors. I know these are kind of light. All right, so you do it from A. And there you go. Now you have a point where 2 angle bisectors meet. Then I'm going to call that E. In this case, E is called the incenter. Okay? All right, now, what does E do? Well, this is where the next part of the construction is going to come in place. I am going to draw a line perpendicular, excuse me, perpendicular from E to segment AB. But I'm going to do a construction. I'm not just going to draw it. So I'm going to turn this paper upside down, just like this. I'm going to put my metal piece on E, and I'm going to open up my compass such that it goes past the line, like this. Now you can see it. Okay, create an arc intersecting that segment twice like this. And then from those 2 endpoints, create an arc from here, boom, and from here, boom. Now, once you do that, connect this point of intersection with E. So what you just created was a line perpendicular right there. Now, there's always a level of error that's going to happen here. So what exactly does this mean? Check this out. From E to that point of intersection, if you did this correctly, which actually mine came out pretty good, I'm not going to lie. Okay, you can inscribe a circle inside. So what does that really mean? It means that the distance from here to here is the same as the distance from here to here, and the same as the distance from here to here. If this point was where the triangle not crossed but touched, and right there, the distance from here to here should be the same as the distance from here to here, and the same as from here to here. That means that E is equidistant to the sides of the triangle. So here, E, the incenter, okay, is equidistant to the sides of a triangle. Okay. Now, if you have an acute or an obtuse, it doesn't matter. The incenter will always be inside. Always inside. Because you're dealing with angle bisectors. Okay. So E is equidistant to the sides of the triangle. Okay. So notice the difference between this one and the previous one. The incenter was equidistant to the vertices of the triangle, and the incenter is equidistant to the sides of the triangle. Okay, two completely different ideas. So make sure not to get them confused. Study these. Okay. All right. Let's go ahead and move on to our examples. Make sure you wrote down where the examples go. Okay, you had problem number 2, which was a graph right there. You have problem number 1 here, problem number 3 there, and in the back you had problem number 4 right there. All right, so let's begin. Now, I'm not very worried if when you're doing this, the copy itself is not 100% correct. Okay, so here, the problem says, zoom in a little bit, 3 snack carts sell frozen yogurt from points A, B, and C outside a city. Each of these 3 carts is the same distance from the frozen yogurt distributor. Find the location of the distributor. So the question is, am I going to use the incenter or the circumcenter? Okay, so what I'm looking for is a point somewhere in the middle that's going to be equidistant to all the carts right here. Okay, the incenter is not going to do that because the incenter is the distance that is going to be, is a point where it's equally distant to the sides. So that doesn't help me. So I don't need the incenter, I need the circumcenter. So what we're going to do is we're going to practice again how to find that. So if you didn't get it the first time, second time, might just do it. Now, of course, it's going to be hard to copy this over here, and I really don't care if you don't copy it, correctly. Just draw a triangle. And we're going to do it again. Okay? A, B, and C. So what we're going to do is a perpendicular bisector of 2 sides. So pay attention. I'm going to do B, BC. Okay, so from B to C, open it up more than halfway. Okay, draw an arc from B. Draw an arc from C. I'm doing it a little faster because you guys have already seen this. Then from there, draw your line. Okay, that's the first one. Perpendicular bisector. Now do it again. Okay, I'm going to do AC now. You could have done AB, it doesn't matter. You get the same point. Okay, so I'm going to make this. Here's the first one. I'm doing it from C. Okay, and then you have those 2 right there, which means that you are going to draw your line from here to here. Boom, there it is. Perpendicular bisector. So this point right here is going to be your circumcenter. And if you were to measure the distance from here to here, notice how you get pretty much the same thing. Okay, look, same thing, same thing, same thing. Okay, so here is where the distributor, we'll call it D, is going to be. Oops. Okay, distributor. All right, and that is example number 1. Let's look at the next one. Okay, for number 2, it says find the coordinates of the circumcenter of triangle ABC with the following vertices. So first thing I want to do is I want to make sure I graph this because I want to be able to do this graphically. It's not too bad. Okay, so let's look at 0, 3, which is right there. Then you have 0, negative 1, which is right there. And 6, negative 1, which is going to be right there. Now, remember what I said. If you have different triangles, you're going to get different results. In this case, I'm going to use a highlighter just because it's kind of light in there. You actually have a right triangle. So remember what I said about right triangles. The circumcenter of a right triangle is going to be on the hypotenuse. The question is, where? For right triangles, it's really, really, really easy. Because all you have to do is look at where is the perpendicular bisector. Okay? So I'm going to pick one side. The perpendicular bisector of a horizontal one, the perpendicular of a horizontal is a vertical at the midpoint. Where's the midpoint between here and here? Right there. And it's going to be a vertical. Like this. Okay? Now I'm going to do the other one a different color so we can see it. The midpoint between 3 and negative 3, it's going to be right there at 1. Okay? So where in the heck is going to be this circumcenter? It's going to be right there at 3, 1. So the circumcenter is going to be at 3, 1. Now you can easily do this with a right triangle. With a different kind, you probably wouldn't get problems like that. But here is where the circumcenter is at. Okay, where the perpendicular bisectors cross. Because look, this one here makes that one congruent. This one here makes that one congruent to that one. Okay, so that is example number 2. Let's look at the next example. Okay, so let's look at what we have here. In the following figure, ND equals 5x minus 1, NE equals 2x plus 11. Find NF, and can NG be equal to 18? Well, first off, I need to figure out, do I have the incenter, or do I have the circumcenter? How do you know? Well, remember, the incenter is made up of angle bisectors, circumcenter of perpendicular bisectors. As you can see, we do have perpendiculars, but as you can see, these sides here are not marked congruent. So we do not have the circumcenter. We have angle bisectors. Okay, so one of the things that we did learn about the incenter is that it's equidistant to the sides, meaning that these 3 sides right here are congruent. We learned that. Okay, so in this case, ND and NE are going to be exactly the same. They're congruent. Okay, so NE is going to be congruent to ND, which means that their measurements are going to be the same. NE and ND are the same. So we already know what those are. That and that. So all you got to do is set them equal to each other. 2x plus 11 equals 5x minus 1. Okay, and then you solve for x. Subtract 2x gives you 11 equal to 3x minus 1. Add 1, and get 12 equals 3x divided by 3, x equals 4. But that's not the distance. They want me to find out NF. So if I find NE or ND, I get NF because, you know, these are actually also equal to NF. So I need to substitute this value into either one of these. It doesn't really matter. I'm going to do it for ND. So NF is going to equal either one of those two. 2x plus 11, you're going to substitute that value in there. 2 times 4 plus 11 gives me 8 plus 11, which happens to be 19. Okay, so NF is 19. So now that's all for part A. What about part B? Part B is asking, can NG be equal to 18? Well, think about this. You have a line, and you have NF. And this distance happens to be 19. That means that this is the shortest distance between this point and this whole line. So anything that is on the side is going to have to be larger than 19. So the question is, can NG equal 18? The answer is no, because any segment coming from N to the whole side has to be bigger than 19, and NG is 18. So the answer is no. And that is example number 3. Let's look at the last one. A city wants to place a lamppost on the boulevard shown so that the lamppost is the same distance from all 3 streets. Hint, hint. Not the vertices, the street. Should the location of the lamppost be at the circumcenter or the incenter? Remember that the circumcenter is equidistant to the vertices. The incenter is equidistant to the sides. The sides of the street here correspond to the sides of the triangle. So therefore, this would be at the incenter. Okay, so it will be at the incenter. Now, I forgot to go over the theorems, but I think you kind of got the point already. Okay, so on page 171, remember that the circumcenter of a triangle is equidistant to the vertices of a triangle. So this is equidistant to the vertices of the triangle. Here, here, and here. And on the next page, it's equidistant to the sides of the triangle. Forgot to mention that. But no, I didn't forget. I said it many times. All right, and that is example number 4. Please make sure you have your full set of notes, and I will see you all later.